YouTube. Okie dokie. Oh, there's Marcos. I apologize for the bird in the background, if y'all can hear it. All right. So on Monday, we covered a decent amount of information. I understand that it was like the first day back from break. So I want to do a quick overview of what we actually covered. That way, for those of you who were kind of zoned out and didn't really catch everything, you can get caught up. Cool. All right. So last time we talked about net force and it being the overall amount of force that's acting on an object. So if there is a net force present, so if I have a value for net force, that means that my object is changing its state of motion. In other words, it's speeding up or slowing down, or changing direction. Because if it's changing direction, then it's accelerating in that direction. So what we did was we did a simulation, and let me pull that up. So we did a simulation with this stuff, and or no, it's this one. Yeah. So we had an object that had a mass of 50 kilograms, and then I applied 50 newtons of force to it, and then the objective that we had over on the screen was we wanted to figure out what the acceleration of the box and the skateboard combined. We want to know how much it was accelerating. All right, Antonio, I got you. Okay. So what we did was we took the value for the mass, which in this case was 50 kilograms, and then we took the force, which was 50 newtons, and we used those values to figure out what the acceleration was. Yeah, so this is live right now, Frank, on YouTube. So you guys can go to my channel and rewatch it. There is a version of this that I did for my fourth block on Tuesday that covers the same material, but I wasn't able to do it for you guys on Monday. Cool. So what we do is, if I have an equation like this, I've got one equation, one unknown. Very simply, if I wanted to solve for A, I divide both sides by 50. It'll cancel on the right side, and 50 divided by 50 is just, it reduces down to 1, and that's how I got acceleration is equal to 1 meter per second squared. Cool. And I do the same process whenever I've got different values. So for part B, I had the same amount of initial force of 50 newtons, but the difference was I doubled the mass. So if I double the mass and I push with the same amount of force, the object isn't going to go as quickly. It's not going to change its state of motion as rapidly because I've got more mass. There's more inertia that I need to move, right? So that means that my acceleration logically should be a lower value than when I had it as 50 kilograms. So if I'm solving for A, I divide both sides by 100. It cancels on the right side. And 50 divided by 100, that reduces down to 1/2. And that indeed is less than the previous value. Make sense? Okay. And then what the third example was, we kept it at 100 kilograms, but then I increased the amount of force being applied by 100 or by 200. So we have a total of 250 newtons being pushed. Where's right here? So the situation that I'm explaining right now is I apply 250 newtons, and then I have 100 kilograms that I was pushing. And then when I hit play, this is moving up more rapidly than our initial situation where I was applying 50 newtons. So notice how this is not moving up as quickly. So this is moving at 1 meter per second squared, or accelerating at 1 meter per second squared. But then for our third scenario, we had 100 kilograms total, and then we had 250 newtons being applied. And then when I hit play, notice that this is going around the speedometer much at a more rapid rate. Cool. So that's all we did with this part. Is there any questions so far? Does everybody feel like they're up to date or caught up? Okay. So then we talked about what the concept of the normal force. Okay. So what the normal force is just the force of the surface pushing back on an object that's making contact with it. And the key to the normal force is that it is always perpendicular to the surface that the object is making contact with. Okay, it's very important that you guys understand that. That's the critical piece of information. So if I have a surface that's horizontal, my normal force would be vertical. Okay, so whether I've got an object being pushed up like this or being set on top of it, it's going to be in the perpendicular axis. Cool. If I have a vertical surface, my normal force would be horizontal. It's always going to be at a 90-degree angle. If I have a surface that's at an angle, it's still going to be perpendicular. So this would be the normal force. Cool. Okay. So what I was explaining in this part here was I was trying to relate the normal force to the force due to gravity, or in other words, or in other terms, we call that the weight. So the normal force, the reason why we know that the normal force in this particular situation is just mass times gravity is because if I have an object that's sitting on a desk or on a table, right? I'll take my Rubik's Cube and then this box. So if I take the cube and I set it on the box, I know that there's a normal force being pushing up from this box that's equal and opposite of the force due to gravity of the Rubik's Cube. The reason why I know that is because I can observe that this cube is not changing its position or changing its state of motion. It's currently at rest, and I can observe that it's not changing its state of motion. It's at rest right now. Still at rest. Still at rest. So with that piece of information, I can conclude that because it's at rest and continually staying at rest, I know that the force due to gravity pointing down, I'll do it in front, sorry. The force due to gravity that's pointing down is being canceled out by the force being applied by the cardboard box. So they're going to have the same magnitude, but in opposite directions. So they're going to exactly cancel each other out. So if an object is not changing its state of motion, we would consider that a balanced scenario. Make sense? kind of like when we were talking about this. So I have one person here. The sum of the forces. There's only one person, so this is obviously not a balanced scenario. So if I hit go, it's changing its state of motion. It was at rest, now it's moving. But if I've got two people over there and one person over here, it doesn't matter how many people are on either side. It only matters what the sum of the forces is. I know that there's 100 newtons going to the left and 100 newtons going in the opposite direction. So when I add those up, I will get 0 because I've got negative 100 and positive 100. When I add those up, I get 0. So this is a balanced situation. So when I hit go, nothing changes. You can apply this in the vertical axis as well. So when I had the cube sitting on top of the box, it's not moving. And because I know it's not changing its state of motion, and because of this example that's on the screen now, I know that if it's not changing its state of motion, the sum of the forces is equal to 0. In other words, it's balanced. So then all of the forces that are acting in that axis will cancel each other out. Is there any confusion about that? Okay. So for that to be the case, the force due to gravity, we know, is mass times gravity, right? Mass times the acceleration due to gravity, because F equals ma, mass times acceleration, and little g is just the acceleration due to gravity. So this is, in fact, an acceleration. So if this is mg, that means that this must also be mg. Cool. But just in the opposite direction. So this would be a negative. This would be a positive. So when I add them up, I get 0. Corey, I got you. Okay. So the next situation that I had was in the unique, like this was a pretty interesting one. So this scenario was I had a box that I was pushing against a wall. So what I had initially was, well, yeah, I'm not going to erase it. So if I had a situation where I just had the surface, I had the box, I was not pushing it into the wall. The wall, of course, isn't pushing back. So we also assumed that it was in a vacuum, so there's no air resistance. So there's just the force due to gravity acting on the box. And if it's just one force, it is impossible for it to be a balanced scenario. I've been using the word scenario a lot. Sorry. Situation. Okay. So if there's only one force present, then it is absolutely going to be an unbalanced situation. So the object will move. And if you think about it logically, if I have a box and then I remove my hand, what happens to the box? The box falls. So in the direction of gravity, right? So in other words, towards the ground. And that was the situation that we had. This one that's on the screen now, I was pushing the box into the wall. So I was applying this force. Gravity is always present, so force due to gravity is always going to be there. And then due to the fact that the box was not morphing into the wall and it wasn't like magically moving away from the wall, its horizontal position was stationary. It was not changing that state of motion. So with that, I know that in the horizontal axis, my forces were balanced. So I know that the amount that I was pushing into the wall was pushing back with the same magnitude, but just in the opposite direction. Cool. Then I posed a question for you guys. I said that if I'm pushing a box against the wall, it's not moving in the vertical axis, so it's not moving up or down, it's remaining stationary. So that means that in the vertical axis, this one here, it's balanced because it's not moving, right? So if it's balanced, I know the forces must sum up to equal 0. And if I know gravity is present, that means that there had to have been a force acting upwards to cancel out the force due to gravity. And what we concluded was this is due to the force due to friction. And depending on the type of surface that the object is resting against, it will be easier or more difficult depending on that surface. So if I had a wall lined with sandpaper compared to a wall that was, made out of ice, it would be more difficult to hold the box against the one with ice than it would be like I would have to push harder to keep the box from falling down. It would require less effort from me to put it against one that has sandpaper because there's more friction with sandpaper. Is everybody tracking so far? Okay. So the last thing that we ended on was talking about this is a diagram. Okay. So where there's a picture of what's going on. And then we were talking about how can we make this a little bit easier to understand. And some of you guys said that what I've got boxed here in blue was easier to understand than what I'm getting ready to talk about. But when it comes to figuring out what direction the overall force is acting, the free body diagram, which is a simplified version of what's actually going on here, is going to be more accurate. So the issue, like this conceptually, will help you understand what's going on. But when we're trying to figure out the mathematics of all this, we have to make sure that we make it into a free body diagram. So the key difference between this diagram and the free body diagram is the fact that the arrows, the vectors of the forces, notice how the normal force and the pushing force are pointing inwards. So when we draw a free body diagram, it's the same thing, but we draw them outwards. So going away from the center. So notice that force push in both the actual figure and the free body, notice force push and force push are in the same direction and they're the same size. Okay? Same thing with the normal force. The same direction and the same size. All right. So that pretty much covers what we did on Monday. Does anybody have any questions? And again, this is being recorded, so you guys can go to my channel on YouTube and rewatch this if you missed any of that. Especially you, Corey, showing up late. Okay. So what I want to talk about today is the force due to friction. Okay. So who can unmute and tell me what friction is? Yeah, so if I rub my hands together like this, what happens? What changes? Yeah, your hands get hot. So whenever we've got two objects that are making contact with each other, friction is I don't want to get too deep into it, but friction is a force that is caused by two surfaces making contact. Cool. All right. Frank. Shh. So here's an example. How many people have um, tried to move a large piece of furniture or like a couch or a bed or something, and it's resting on carpet? And let me know if this is something that you've experienced. So when you are initially trying to push the piece of furniture, is it more difficult to push it when it's before it starts moving or after it starts moving? When it or Yeah, it's more difficult before it starts to move, right? So when to get it to start moving, it feels like it's a lot more difficult than if it's already sliding, right? Yeah. So when we talk about friction, there are actually two types of friction. There's static friction. That's the friction that is dealing with objects that are at rest or that are not moving. And then there's kinetic friction. Kinetic friction is friction of motion. No, so it's not static electricity. It's just like static as in stationary. Cool. All right. So when we talk about friction, zoom in a little bit. So the force due to friction, and I'll show you guys how I do the little F. So it looks like a little weird S, and then I put like a little horizontal line on it. So this is what I refer to as a script F. So the force due to friction, and I'm going to go ahead and just give you guys the equation, is going to be the coefficient of friction. I'll explain what that is in a second, multiplied by the normal force. Okay. So I'm going to write what these are. So this is the force. Get a smaller pen. So that's the force due to friction. This is the coefficient of friction. And then lastly, that is the normal force. Okay, so let me explain what on earth this is. Okay. So the coefficient of friction is, in the easiest terms, how frictiony a surface is. Okay. So when I have something that's very has a lot of friction, that's going to be something that has a high coefficient of friction. Something that is very smooth, very slick, a very low amount of friction, that's going to have a low coefficient of friction. Does that make sense? If something is smooth, it's a low value. If something's very rough and very frictiony, it's going to have a higher value for the coefficient of friction. Okay. So one of the key things with the coefficient of friction is that the value is going to be greater than 0, but it's also going to be less than 1. So it's going to always be 0 point something. Okay, some number. But it's always going to be 0 point something. And the symbol that we use to represent the coefficient of friction is this symbol here. Okay, so if you guys are trying to write this down, it's like a U, but with like a little front tail. Cool. So what I do is I kind of go up like this, and I just write the letter U. So this is the Greek symbol mu, mu. Is everybody tracking so far? Okay. So, like I mentioned a second ago, there's 2 types of frictions. And because there are 2 types of frictions, there's going to be 2 types of coefficients of frictions. So there's going to be mu sub s for the coefficient of static friction. And then there's going to be mu sub k, which is the coefficient of kinetic. And if any of my writing gets blocked out by the by my little picture down here, let me know. Okay. So knowing that, my force due to static friction, so F sub F, comma S. So this is the force due to static friction. And then force due to friction kinetic. Correct. See, it's pretty easy, right? Okay. So I'll give you guys a second to copy that down. Okay. Is everybody good? Okie dokie. All right. So here's an example. I want to know the amount of force required for an object to start to move. Okay, how much force do I need to apply, either pushing or pulling? How much force do I need to exert in order to get this object to begin to move? Right? So what's the maximum amount of force that I would need? So that's what the purpose of this example is. Muck. How much? So how much force is required? And I apologize for how messy this is. I'm trying to get through this quickly. So how much force is required to begin to start to move an object? Cool. All right. So I'm going to set up the scenario. So here's my surface. My box. Okay. So in this situation, I'll call this surface. So if I have an object and we're assuming that we're on Earth, what do we know immediately is acting on this object? Objects have mass. Correct. So we know that the force due to gravity is acting on the object. So gravity is going down. Force due to gravity. Cool. Who just came in? Antonio. Oh, somebody popped in, but okay. All right. So if what's happening is I'm going to be pulling on the box, and I want to know how much force I need to pull with in order to get it to start to move. Okay. So this object, we're going to be given that the object's mass is going to be, we'll say 10 kilograms. So that's given to us. And we're also going to be given the coefficient of static friction. So that's going to be mu sub s. And that's going to have a value of 0.8. Now, one thing to remember or to note is that the coefficients of static and kinetic friction do not have units. What they are, they're essentially just a ratio that we use to figure out how frictiony something is. I'm not going to get into all the details about it because I don't want to give you guys too much information and potentially confuse you. But just know that there's no units with it. Okay, so that's why it's called the coefficient. It's just a number. Cool. And remember, this number is always going to be greater than 0, but less than 1. Okay. And then since we're dealing with gravity, we can also put in here, and remember in my class, to keep the math simple, we're going to use 10 meters over second squared for the acceleration due to gravity. Cool. So when we're creating our diagram, our figure, I would recommend not putting equations or numbers into it and just drawing the vectors and putting in the variables that represent those vectors. So if we think about this logically, 12, 10. Sorry, what I was trying to do, I was trying to make the scenario like this. Let's do this. Let's modify the mass here. let's make that 50 just to kind of match what we're doing over here. So the situation is I've got a 50 kilogram mass, in other words, this box, and I know the force of gravity is going down. And then I'm going to be applying a force. In this case, I'm pushing it. I don't think I can I pull it? No. All right, so get over here. Reset. So I'm going to be pushing it, and I'm going to apply 50 newtons. Okay. So the object is we need to figure out how much force is required to get it to move. I don't know. I wish I could set how much friction value it is. So we'll say right about here. So that's about 80%. So this would be 0, this would be 1, and the 0.8 would be about right here. Cool. So I'm hoping this works. So I want to know what number should I have here in order to get it to start to move. Make sense? Now, if I go back to my figure, I know that the box, like when I hit play, the box is not moving, right? It's not moving horizontally and it's not moving vertically. So if we start off with the vertical axis, I know gravity is going down, so there must be something going up, and that's going to be the normal force. That's going to be the force of the surface pushing back onto the box. So that's going to be in the vertical direction. So I need to represent that. So this is the normal force. Cool. And then if I'm going to be pushing the box, do purple. So this is going to be force push, and that's going to be in that direction. So if I push the box, but I'm not applying enough force, is the box going to move? So the direction wouldn't matter. But if I don't apply enough force, it's not going to move. That's what I was getting at. Say again? Yeah. So then I would have to add more force, right, in order to try to get it to move. Yeah. So I would have more newtons. So if I apply force, notice right now the sum of the forces is equal to 0. That's because the amount of applied force, the 50 newtons, is not strong enough to get it to move. So that means that it's getting canceled out by the force due to friction. And if I look, applied force is going to the right. I'll look back over here. Force push is going to the right. So that means that the force due to friction is going to try to resist that motion because the object's it's going to want to go to the right. It's going to want to go in this direction, but friction's like, I ain't trying to hear that. So it's going to be pushing back. So friction will be pointing, come on, in that direction. So this is going to be force due to static friction. Is everybody tracking so far? Okay. Now, it goes a little bit smaller. I know that in the y-axis, the sum of the forces in the y-axis must add up to be 0. Make sense? So I know that the force due to gravity is going to be the same number as the normal force. They're just going to have different signs. Make sense? So I know that the forces in the y-axis, or how about this? The net force. So remember, net force is when I add up all the forces, the sum of the forces. So the net forces in the y are going to be the force due to gravity plus the normal force. Make sense? And when I add those up, I'm going to get 0. And let me keep the colors the same. So force due to gravity, and then normal force. It's blue. Okay. So if I add up the force due to gravity and the normal force, they should equal 0. Okay. Now I know that the force due to gravity is equal to mass times gravity. Cool. So the force due to gravity is going to be a negative value. Okay. So if I look at the direction of that, that's pointing down. So that's going to be negative. So if I do negative force due to gravity, or how about this? We'll do this. So if I don't know what the normal force is, and I've got this expression here, the force due to gravity plus the normal force is equal to 0. Force due to gravity, I have an equation for that. But for the normal force, I don't have an exact equation for that. So I want to know what the normal force is. So the normal force, if I take this equation right here and I solve for the normal force, I just subtract force due to gravity on both sides. So the normal force is just the opposite of the force due to gravity, which is what we've discussed before. Cool. And I know that the force due to gravity is just mass times gravity. So then we're going to have negative m times g. And that's going to be my normal force. Okay. So for right now, like if I gave you guys this question, I will typically give you like part A, part B, whatever, to kind of help you along these problems. So for this situation, for part A, I'd be like, what is the normal force? I have the value for the mass right here. And then I also have the value for the acceleration due to gravity right here. So then you would be able to give me the value for the normal force. Is everybody tracking? So this is going to be the net force in the y-axis. Now let's take a look at the x-axis. My goal in this problem, was to figure out what force push is. That's my find. Find force push. So I look at all the forces that are in the x-axis. So F net x is going to be equal to force push plus the force due to static friction. Now, I know that in this simulation, if I apply a force, that force is going to be counteracted by the friction force, and the sum of my forces is equal to zero. So that means my net force, that's another way of saying the sum of the forces, my net force is zero. There's nothing left over. It all gets canceled out. So I know that all of this equals zero if I add these two together. So just like before, I've got this equation, and my goal is to solve for force push. So let's go ahead and do that. Let's solve for F push. So F push is going to be equal to, oops, do it in black, the negative of the force due to friction. Does that make sense? We know from before that the force due to friction is just going to be mu times the normal force. Mu sub s multiplied by the normal force Is everybody tracking so far? So this part right here is the force due to static friction. Okay. And I don't have a value for the normal force, but because we kind of already found that in the y-axis, I can take whatever that's equal to and substitute it in right here. So the normal force is just going to be negative m times g. And put that in parentheses or square brackets. And then mu sub s I'm hoping the colors are helping you guys. So if I get rid of all the multiplication and all that kind of stuff, let's clean this up a little bit. So I've got a negative mu sub s times a negative m times g. What happens to the negatives? The negatives cancel. So what I end up getting is just going to be mu sub s, the coefficient of static friction, times the mass, times the acceleration due to gravity. That, my dear students, is how we find the force required by pushing to get, drop my pen, to get the box to move. So if I gave you guys values for this, which I do, so the mass is going to be 50. And so I get 50, then 10, and then 0.8. So it's going to be 500, so 80% of 500. I don't know why I needed a calculator for that. It's just going to be 400 newtons. So 50 times 10 is going to be 500, and then times 0.8, that's just 80% of it. So the amount of force pushing should be about 400 newtons. Cool. So if I did this correctly, like I wish there was a way that I could actually put in the coefficient of friction. This should not move until I get up to 400. Yeah, it doesn't look like it's the correct units. Maybe. Close. Hold on. Say it one more time. If I add more force, am I going to get stuck to everything? That may have been like what force was like what was the force being caused by? Hmm. So I'm assuming what. Okay, so what I'm thinking may have been what they were doing was they were possibly modifying gravity, um, like changing the amount of gravity that each object had. Um, but it wouldn't. I mean, just by applying a certain amount of force to something won't make other things stick. Like, like if I apply a force to my desk, it's not going to change something that's over on the other side of the room. You know what I mean? So forces only deal with objects that are interacting with each other. Cool. All right. So what happened was I had it on pause. So let's see. Okay. Yeah. So this isn't actually correct. I wish there was a way I could actually put in the coefficient of friction. All right. So what I want to show you guys here is I'm applying 250 newtons of force. As of right now, the force due to friction is only 154 newtons. Okay. So let me go 188. There we go. All right. So right here, let's do this. Okay. Let me wait for it to stop. All right. So what I want to show you is if I apply a certain amount of force. So I've got 151 or 150 newtons, and it's still some of the force is equal to zero. But if I go up one little bit, let me pause it. So if I go to 151, there we go. If I hit play, notice it's not moving. If I go 52, 53, 54. All right, so watch this. Take note of the amount of force that I'm applying. 70. Oh, there we go. All right, so I don't know if y'all saw that. Let's pause. All right, so 200. All right, I went to the stops again. All right, so I didn't know when it was going to actually kick over. So I'm going to go all the way up because the thing was like right at 200. Okay, so what I want to show you guys is the amount of force of friction right now is almost 200, and it's stationary. The amount of force that I'm applying is 199 newtons. Once I go up to 200, watch this number. Okay, so if I go up to 200, maybe it's 201. Yeah. So what happened to my force due to friction? Yeah, it dropped dramatically, right? So what happened was the maximum amount of friction or amount of force that I could apply to the box was 200 newtons. Like that was the maximum. So 200 newtons. Let me stop the force. Play. Wait for it to stop. So right now the only force that's acting on is friction, and it's acting in the opposite direction of the motion. So then it starts to slow it down. So if I apply 200 newtons, this is the static friction. Okay. So when I was mentioning before, static friction is always going to be a higher value than kinetic friction. So if I wanted to figure out what value of static friction I've got right here, we could do that too. Maybe we can do that on, I'll see you guys on Tuesday, right? Yeah. So on Tuesday, what we'll do is we'll talk about how to solve for the coefficient of friction, whether it be static or kinetic. And it's going to be very similar to what we did over on this page, where we try to figure out the maximum amount of force being pushed. But hey Frank, can you mute for me? Thank you. So what I want to do is I want to show you guys how to figure out how to solve for the coefficient of static and kinetic friction by knowing what the amount of force that's being applied, knowing the mass, and the acceleration due to gravity. Cool. And when we do this on Tuesday, what we'll do is we'll just use 10 for the acceleration due to gravity. Cool. And I'll live stream it so you guys can watch that one too. All right. So I'm going to go ahead and stop the live stream.